And while we are waiting for people to come, I'm going to ask you to tell me what you see this. So please come to the front. I'm going to ask you questions. What do you read? What do you see there? What text can you see? Yeah? What text can you see? Anything? Yeah. Omkar. She says Omkar. And what do you see? Yeah, we'll focus on Omkar now. And what did you see? Omkar. We'll focus on Omkar. Alright, what do you see? Please come in. What do you see? Omkar. Very good. Now there is a story of Arjuna who was asked to shoot a parrot, and many people said, what do you see? And Bhishma came in, and I'm going to be here, okay, so please come forward. You should be able to read this. It says here, Harry Potter and complex numbers, coming to you very soon, okay? So you're going to listen to me about complex numbers, believe it or not, today. So, back to Arjuna, right? So when he was looking at the parrot, Bhishma came and said, what do you see? He said, I see leaves, I see trees. Yudhishthira came, he said, what do you see? He said, I see truth, right? And he sees many other things. And what does Arjuna see? Only the earth. When I see this bottle, I see Omkar, but I also see, through Omkar, I see an inverse Omkar, right? Did you see the inverse Omkar? Can you tell me, can you describe the inverse Omkar? See through it, through the bottle. You want to see it like this? Can you see that? Yeah. Try to see. It's there. Okay? You can't see it. Like, can you see the inverse Omkar? Yes? Okay, good. Did you see that? The inverse Omkar? Can you explain the difference between this inverse Omkar and this inverse Omkar? Is there any difference? What is the difference? So, very good. She says something. She said, I saw Omkar in both the places, but
one is larger compared to the other.
Excellent. Right? So, this is what we're going to talk about. Omkar, never heard of this guy, but Omkar and why is the Omkar here different from the Omkar here? Same bottle. This is empty, this is full, and because it's full, there is refraction going on, and there is, well, the refraction manifests itself as a ulta Omkar, and it's larger because of, it acts like my chashma, acts like a lens. What's the lens maker formula? All you people who just finished 12th and so on, right? You know the lens maker formula. 1 by u or y, it's confusing. 1 by v minus 1 by u, 1 by u minus, right? Happens to me all the time, right? So in my exams, I allow people to write formulas so that they don't remember these things. And today we'll have a quiz at the end of this, okay? Alright? Okay? So that's the plan. The plan is to be interactive. The plan is to talk about rendering. And the plan is to be engaged with you. At the same time, we want to cover the topics that Professor Prem Kalra nicely set up for me, which is modeling objects, shape modeling. And after we have the modeling, we want to be able to model Omkar, but we also want to be able to model inverse Omkar, slightly larger. And how does computer graphics do these things? How does computer graphics give you the same illusion that works for you when you see with your naked eyes or with spectacles, right? What is that? How does it work? Right? That's the plan. So let's pull up the slides, and I'm going to, as I said, use the board. So count down, or be ready to face questions at the back. Alright? Come, there are some seats here. Okay? Okay, so let me pick up from where Professor Chandran left off. My name is Sharat. I am in the Computer Science Department at IIT Bombay. And we want to talk about rendering. So the structure of this tutorial, right, is going to be like this. Okay, my keyboard doesn't work. Let me see that this works. Okay, so it's about rendering, and before I start out, I want to thank the organizers of NCVPRIPG, various people, too many to mention them, for giving me this opportunity to talk to you. Okay? So, with that, thanks. Let's go on to the structure of today's presentation. So, there are 3 parts in it. If you lose focus in one of them, you can go to sleep, you can come back, I'll tell you again when we restart so that we don't miss anything. Alright? Always happens. 1.5 hours, kind of a long time to keep your attention. The second part of this tutorial is that it's not a research talk. So you'll hear a lot of research talks in the next 2 days. And my talk is a tutorial. It's not a research talk. So a little bit slow paced. Hopefully at the end of the day, you will get to learn 1 thing or 2 things that you will remember 3 months from now. No guarantees after 3 months. Okay. But you should remember something that I said 3 months. And one of them will be complex numbers, but that will be after lunch session. Okay? So Harry Potter and complex numbers coming to you after lunch. Okay? So the content is easy to get on the internet. So what I'll try to do is complement that. Try to talk about my experiences so that you can sort of get some perspective. Ask questions. Where is the microphone? Cordless microphone for the audience? Okay. So you can give it to me. I'll keep this with somebody. Ask questions. Interrupt me. It was a wonderful session towards the end of the last talk. Embarrass me. Okay, that's your challenge. You want to ask questions that I cannot answer. Right? Keep it with you as a representative. But embarrass me technically. Okay, not otherwise. And we also see a little bit of math. Okay, little bit of math that you hated in school. You said, why do you have to study complex numbers? What good is imaginary numbers? What good is imaginary numbers? Why did we study them? Right? A little bit of math, we'll talk about that. We talked about differentiation. We'll talk about integrals. Why did we study them in our 11th, 12th? It's so tough getting through to engineering. Right? Remember those days? Yeah? Going to coaching classes. Alright, huh? All that kind of stuff. So, it pays off. It's useful. So, I'll just refresh some of that. Okay, that's the plan. Any questions? So, in rendering, we're talking about 3 things today. One is visibility. The second is ray tracing. And the third is the tools for animation. And in the tools for animation is when we will use complex numbers. Actually, we'll use something more than complex numbers. Okay? And that's going to be really fascinating. But, I'm holding that to the end. Only people who really want to hear that should, will wait for it. Okay, what's the visibility problem? Visibility problem is, now you see the cell phone. Please keep it on. Please keep it on. And put it in record mode. And it's silent. Alright? Okay. So when we model this inside the computer, either using meshes or, look at this curve here. It's nice and easy to hold. That's a parametric spline. Right? We want to be, when we model it like this and we put it in the computer, we can go ahead and render them. But the computer does not know about visibility. So if you put it behind, you don't see it, but there's nothing that prevents the computer to draw me first and then draw the cell phone after me. And so the cell phone will appear as if it's right here. Right? So we want to be able to solve the visibility problem. The visibility problem is to figure out what is visible. Right? If you ask me a tough question, I'll go behind this and you can't see me. Right? I'm invisible to you. Okay? We want to be able to do that inside the computer. Okay? That's the visibility problem. And the visibility problem manifests itself in many ways. Also, when we trace rays and see this upside down Omkar, right? And larger Omkar, we've got to figure out what is visible and what is not visible. Okay, so let's see. We'll dive into it. So these three parts: visibility, ray tracing, and tools for animation. This is the simplest, visibility. This is also quite simple, but a little bit more math. And when we come back for this specific tool that I'm interested in today to talking to you, it'll be also simple, but it'll be at the end of the day, so you'll have to focus at that time. Alright, so the visibility problem. Right? I just explained the problem, and there is a very simple solution for it, and it's called the Z-buffer solution. So if you go for an interview for your replacements and you say you do graphics and you don't know the Z-buffer algorithm, they know you don't know anything, right? They're not going to give you a job. So that's like the bread and butter algorithm. So I call it depth buffer algorithm, Z-buffer. Then we talk about something a little bit more interesting, which uses your data structure scores. It's called the BSP algorithm. Those are the two parts in my first part of the talk, which is about visibility. Is that okay? Right. So here we go. We see an object, and unlike the beautiful pictures we saw earlier, I have described that object in terms of a bunch of polygons. Right? There was a question about that auger, which was, is it rendered using parametric curves or was it using a mesh? And this is, a mesh is made up of polygons. I just a soup of polygons up there, and I'm telling you, I'm looking at it from here. Okay? So this is a meta picture, right? It was a wonderful meta picture that he had shown earlier in the presentation. Here is another meta picture. We're looking at this box, and we're seeing this. You pretend that the camera is looking at this, and you want to figure out which polygon is visible. This is the basic idea, right? It's a bread and butter thing, right? We want to be able to do that so that all the effort that goes into shape modeling doesn't get surprised by it. If you don't do it the right way, the object will look like this. It's kind of hard to read this object. If you do it the right way, it looks like this. Right? You can make sense of it. What's the difference? The computer has rendered all polygons. There are about 20 polygons in that. It's rendered both polygons there. And here it's done the right way, here it's done wrong. Right? How does the computer do that? We take it for granted when we see the games, video games, when we see any movies. Visibility is bread and butter. Right? The visibility problem is more complex from a computer science point of view than other problems, because the visibility problem, what is visible is a function of other points. Let me explain this to you. If you think about, let me try to explain it again. Right? If you think about drawing a B-spline curve, the complexity is linear. If there are n points, you draw it in linear space, linear time. If you talk about a visibility problem, you've got to figure out, hey, is this visible? And my visibility depends upon everybody else. My visibility depends upon you. Your visibility in turn depends upon something else. So it's technically more complicated. Although from an understanding point of view, it's trivial. We'll do the trivial algorithm in just a minute. Alright? So that's what we're trying to do. We're trying the visibility problem. So this is a very easy way of doing it. Right? And in addition to the graphics card shows you finally what is rendered. This could be the NVIDIA card or some other Radeon card or ATI card or something like that. Or Intel's built-in. So built-in motherboard comes with a graphics card, right? Graphics capability. It doesn't have a card, but it's a graphics capability. So that there's a buffer there. The buffer, the hardware text, whatever is there, some color, red, blue, green, whatever it is. Right now, PDF viewer is doing that. Whatever is there in the buffer, it puts it up for display. But in the depth buffer algorithm, there's another buffer, invisible buffer, sitting there, which decides what goes into this buffer. Right? So that's the Z buffer, and it's going to have the depth values stored. So what is a polygon in the 3D world? It's a bunch of points, X, Y, Z, like we saw in the case of splines. Each point, there is an X, Y, Z here, there's an X, Y, Z here, there is a statement somewhere which says this point is connected to this point, and so on and so forth. And finally, you get the object. So what we're going to do is we're going to render a polygon. What does that mean? Forget about rendering many polygons. We're going to render a polygon. What does that mean? First of all, we take a polygon and chop them up into convex objects, triangles, or squares, quads as it's called. Let's not call them squares, let's call them quads. What's a quad? It's a quadrilateral, right? So a bunch made up. Why is a quadrilateral nice? Because it's generally convex. So let's just think of them as triangles, right? So we take up this polygon, divide them into triangles. That's called a triangulation problem. Given a polygon, one polygon made of n points, make them into triangles. Given a triangle, now that there's a triangle living in 3 space, so you must imagine all your games, every single one of them, right? Doom, Quake, whatever, right? NFS, Speed, right? Nintendo Wii, all of them has inside a mechanism that takes a triangle which is in 3D, X, Y, Z, X, Y, Z, X, Y, Z, and makes it 2D, right? With an illusion of perspective depth, so it looks like you're watching the scene. So I'm not going to talk about that aspect of how you take a 3D polygon and make it 2D. But let's suppose you have it, the rendering step, here's a triangle, the rendering step somehow will fill all these intermediate pixels and basically shade them. And that's called scan conversion, for example. Right? All of these are multiple words, scan conversion. Take a triangle in 3D and figure out, is this point inside the triangle or not? And let's say it's a blue triangle, you make it blue. Okay? Now, if you were to take the second triangle and do the same thing, let's say that's a black triangle, then you're going to get a structure like this. Now, you should imagine that these are all nice, wonderful shapes of people or characters in your favorite video games. But at the end of the day, this is what is happening. Right? Now, if you did the wrong way, let's say the blue is supposed to come before the black from a particular viewpoint. This is very important, right? From a particular viewpoint. From his viewpoint, the podium is invisible. From her viewpoint, the podium is visible. Right? I'm blocking it, right, for him. So from a particular viewpoint, if you're looking at this, then what will you do? It's a very simple algorithm. You create a buffer, right? And you can convert the blue triangle inside your buffer, right? So this is the hidden buffer, and this is what people see on the screen. There are 2 buffers. This is the one which is all the time being shown by the hardware onto the monitor, and so constantly being refreshed every microsecond, right? So it says 60 hertz when you do a graphics card, say something about that. So it goes very, very fast. Right? It's getting buffered. So this is the hidden one. So you take this triangle, convert. Okay, scan convert. There are several algorithms on that. In your basic computer graphics, you learn how that is done. Okay.
Buffer is in 2D and triangle is in 3D.
Excellent. The buffer is in 2D. The triangle is in 3D. So we do the first step of taking the 3D triangle from a particular viewpoint, show the sense of perspective depth, in the sense that if the triangle is far away, it's going to look small. This triangle of a similar dimension is close by, it's going to look big. we do that computation, and then we finally paste that triangle, so to speak, onto this, right? This is not the visibility problem. This is the problem of taking a 3D triangle, putting it onto a screen so that it looks, it's basics, like 001 of graphics, right? It happens like that. In the visibility problem, we take the second one and we draw it, but now every time, well, before you draw it, you ask what is the depth of each particular pixel, right? So you initialize the buffer with depth equal to infinity for all points. You place the blue triangle. Now the depth buffer is updated with the depth for the blue triangle. It's the true depth, not the depth on the plane. It's the true depth, right? And so now, at this point, all the depths are there. Okay? And then so Turbo C++ will not do that for you. Turbo C++ will just render a triangle. Okay? Your basic CS101 kind of course you did, that's what that will do. OpenGL will render this, and when you take the next black triangle, so first when you put the blue triangle, you update the depth at every point. You have a blue everywhere, but in addition you say depth at every point, the true depth, and it's going to change at every point. Then you put the black one, and then when you put the black one, you update the depth buffer. And you say, is my depth less or more? Okay? So the basic model of computer graphics is like the camera that you see behind you. There is an eye, or the center of projection. There is a plane, and there is an object. And then we decide what needs to be painted based on that. Alright? So now we have updated the depth buffer. When the black comes, the depth buffer is updated. Depending upon which one is first, either the blue will come out winner or the black will come out winner. And so if the black is not supposed to be a winner, then that buffer will look like that. Is that okay? That's the depth buffer algorithm. Okay? So when you go to the BIOS, somewhere there it says, right, main memory. Nowadays nobody looks at the BIOS. In the olden days people used to look at the BIOS screens, right? But if you look at it, you will see somewhere there is graphics memory. Okay? And when you have graphics memory, that memory is allotted for something like this, right? For this as well as for that, so that we make sure that there's enough memory for things to happen. Alright, so that's the depth buffer algorithm. I've just shown you an example here in 2D. We have a bunch of 2D shapes now, and there is an eye. And we may imagine that there is a viewpoint, there's a view frustum, view cone if you like, and for example from here, we will not be able to see this point because it's not in my frustum. So like the camera cannot see the one that's recording me. It can see this point and this point, whereas he unzooms, he won't be able to see that gentleman at the back, right? So there's a frustum there. So that frustum will first take away all these points, right? And then it has a new bunch of polygons, okay? And then those polygons are then scan converted one by one, and you will get a rendering. Alright? So this is a standard algorithm. This is the pseudocode, which says for each polygon and for each pixel covering the face, update the depth, compute the depth. If the depth is less than the existing depth, update it, and so on. Right? Four lines of code. So I said that this is the most complicated algorithm, technically, but we see there's 4 lines of code which essentially does this problem, and that's because it does it in screen space. Okay, what do I mean by screen space? It does it, for example, this screen is 1360 by 766. So it's doing this only up to that particular resolution. If you were to zoom in, then you've got to redo the whole thing, otherwise the system will not, it'll give you wrong colors, so to speak. So, I'll come back and talk to you about this technical aspect of why this is most complicated later on, but just keep the two things in your so what is the advantages? Advantages, lady with the mic, advantages? Something, quick. Simple. Okay. Disadvantages. You forgot. Now you have to answer the disadvantages. What's wrong with this algorithm? Why is this a difficult problem? What is the problem? Think of some problem. Sure you can think of some problem. What is wrong? When will this algorithm fail? Right. If something is transparent, remember Omkar, it will not work because when you update the depth, what is the meaning of the word depth of a transparent object, right? So there are ways of solving it. I'll come back to that later. Any other disadvantages? Different viewpoints. Okay, there are many more, but that we'll take that as a cue. You lost your mic to the gentleman there. Okay, keep the mic with you next time. All right, you challenge. All right. Okay, score 2-0. Okay, all right. 2-0. Slytherin versus. Not Slytherin? Okay. Alright. Okay. So the next algorithm is what we call as the BSP algorithm. Slightly more complicated. And it addresses this problem of dynamically updating the viewpoint. He said the viewpoint, right? So we saw that if I'm standing here, you render it, as soon as I move away, the system has to render other things, right? So it has to update it, right? So, yeah, computers are very fast, we can do that. But as mentioned earlier in the morning talk, now the problem is data is getting tremendously large, right? Millions of polygons coming, right? And we want to be able to handle that capability in some way. Let me show you a small video for those who are falling asleep. Right. Let's see. Okay. So here is hopefully I'll take that. Okay. All right. Okay. So here we see a scene which has 13.5 billion points, right? And we are walking through this. As we walk through it, things keep changing, right? And we want to be able to handle this at real-time performance. Any game that you played, NFS, whatever, right? Movement is the essence, right? You're going levels, you're changing things, and so on. You want to be able to do that, okay? So, so what do we do? So how does Google work? It's got terabytes of data, petabytes of data. How does it work? How does it work? How can it give results instantly? Type in NCVPRIPG, comes. Right? Comes from some database. To half, keep going. What is it? Cache. Indexing. Right? So it's pre-processing. You want to pre-process the data, right? Google is not sitting there, giving you the results of now, right? There are some special algorithms to handle the now case. But right now there is a breaking scene, they handle that separately. But by and large, it takes some time, let's say half hour or something like that at the very least. So although they have, essentially, about 1 million computers, maybe more, the pre-processing is necessary. Okay? So this algorithm, which I'm going to talk about, the binary space partitioning tree, is a mechanism to pre-process the data. Okay? So you pre-process the data, and then you do the rendering. So here is the basic idea. You take a bunch of polygons, and you sort them. Okay? You sort the polygons. Yeah? Question? Okay, sure. Good point. So that's what I said. Rendering means to take care of these objects that he has carefully constructed. Professor Kalra carefully constructed those polygons and shapes using Bezier curves and B-splines and volumetric rendering. Idea is to show that, so that you believe that that object really exists in front of your eyes. Okay? When Adobe Photoshop loads an image, okay, it takes a pre-rendered, some camera has taken a picture and just shows it on the screen. That's like the zero definition of rendering. You have a photograph on the disk, it's a JPEG file, you put it in there and then you do some editing. When we talk about rendering in graphics, we are saying we don't have an image, we generate an image for you. We take a description. Mathematically, there are complex numbers inside it. There is a function, implicit function, there's a function, there's a Bernstein polynomial sitting there inside the computer. That Bernstein polynomial appears as Harry Potter. That's rendering. You take the map, convert them into triangles, polygons, make them into triangles, show them on the picture, and then you believe that this is Harry Potter. Right? So the process of doing that in a photorealistic way, as if a camera had taken a picture, that process is called rendering. The process of synthesizing a picture, given an abstract description of the objects, and putting it on the screen so that you cannot distinguish that from real, that process is called rendering. Which means that if in reality this appears ulta and you see a magnified Omkar, we got to do that. We got to have algorithms which will do that. That's a rendering algorithm. If in reality you cannot see this bottle because it's behind you, this physically solves the visibility problem. But we have to have an algorithm which will solve the visibility problem, so that then it does what we expect it to do. Alright? Please feel free to interrupt me. Okay, this is a tutorial, it's not a research talk. Okay? Right. So we're looking at this method of pre-processing this polygon, which is sitting there. And we want to pre-process them. And we want to do something like sorting, right? This is the algorithm that you learned in engineering, right? Sorting. Everybody learns sorting. Given a bunch of numbers, sort them. Write a program to do that, right? Quick sort, bubble sort. One more example. Visual sort, right? That's what we're going to look at. So you want to take a bunch of polygons, think triangles, and arrange them such that, given a viewpoint, this viewpoint and that viewpoint, we can quickly generate what is the correct order, okay, to solve the disadvantage of the Z-buffer algorithm. Okay, for the walkthrough example, whenever I'm walking through, I'm seeing different things. First, I see these ladies here, now I don't see them, right? I want to be able to constantly update what I see, right? Now I don't see them. So we want to be able to do these kinds of things, right? So here is the beauty of this algorithm. Okay, ready? The problem? Okay. Here's the beauty of the algorithm. And that's why I love it, right? It doesn't ask you what is the viewpoint. It's just going to pre-process them. But when given a viewpoint, it will sort them correctly. Okay? Remember this example, right? In this case, the blue polygon, the blue triangle is in front. So it's sorted means this is in ascending visual order. Where? Seen from you. If I see from the back, the black is first and the blue is later on. Right? So we want to be able to, and now you know, triangle in 3 dimensions is going to be more complicated. And we want to be able to do that. And we'll do something that you know in second level computer science, right? Pre-order traversal. We're going to use pre-order traversal, in-order traversal to solve this problem. Okay? That's why you learn in-order traversal, so that you can understand this. Okay. So first of all, what is the problem? Arrange polygons in order. What order from which viewpoint? Doesn't matter. Strange. Okay? Hang on to that point. And sorted order means that it'll produce a list of triangles, okay, such that, and a data structure, such that given any viewpoint, we'll be able to. So it's difficult to solve because we don't know the viewpoint in advance, okay, but the algorithm will turn out to be simple, okay. So here is the idea. So sorting may be attempted by some very simple ways, but it won't work, right? For example, in the figure, A, the sorted order is what? Let's say A is at the back and B is at the front, and then what we're going to do is we will not use a Z buffer. We'll just paint B. We'll paint A, then we'll overpaint B. But because it's in sorted order, we are guaranteed that it will look nice, it will look correct. Okay? This is the idea. Following this? Okay, so how do we sort them? You may sort by, let's say I sort by the Z value of polygon A. Can I say if the Z value of A, this point, is more than the Z value of B, then the polygons are sorted such that B is less than A? Can I do that? You're nodding your head saying no. Why not? It's not always, right? So you want to, it could be the case that one vertex may be far away, but the other vertex could be close by. So how do we handle this, right? So this is a problem, okay? More difficult than the normal sorting problem of sorting integers and things like that. Okay, so let's see. And it's very troublesome, right? In fact, there is no sorted order. For example, let's take this case, right? In this, from the way I've drawn these dotted lines, it appears that P is in front of Q, Q is in front of R, and R is in front of P. Right? So there is no sorted order because P is less than Q is less than R is less than P. So that doesn't work. Right? So what do we do in these kind of cases? Here's another case. Right? You can construct any number of such cases. Right? P is less than Q, Q is less than R, R is less than S, S is less than P, right? Any number of cases we can create. Really troublesome. So we're going to solve this troublesome problem that will outperform the Z buffer algorithm because it will give a new feature that is of pre-processing, but it's all a difficult problem. Want to learn this? Right? Simple, cute algorithm. Here's how it works. Okay. First thing is that there is a concept of cutting coming in, right? We won't cut all the polygons, but sometimes we'll have to cut a polygon. So for example, here there is a vertex, there's a polygon V1, V2, V3, V4, V5, which is sort of in front of this quadrilateral. So there's a pentagon in front of this quadrilateral, but the pentagon is also behind the quadrilateral. So we need an algorithm which takes a polygon, another polygon, and cut the polygon. Okay? So this we have seen in 10th standard and so on. How do we take a line? Suppose I have a line, and I want to find out what is closer to the origin and further from the origin, right? So sort of if you know these endpoints, then it's possible for you to sort of return a new endpoint. So you can return, given AB and CD, you can return AX and XB such that AX is closer to the origin and XB is further from the origin with respect to CD. Right? You can do this. You've done this before many times. Right? You can do that. We want to do that in 3 dimensions. Okay? So the algorithm is not too difficult. I'm not going to go through that algorithm, but it's a basic math algorithm. You will take, for example, this line segment V2, V1, V2, and let's say V1 is closer to the origin and V2 is away from the origin. You sort of figure out this intersection point. To figure out this intersection point, V2, V3, you will find out there is no intersection point. Both points are completely on the other side of this polygon. V3, V4, this point is such that the equivalent of that X, right? And then given V1, V2, V3, V4, V5, we'll output 2 polygons. V1, X, V2, V3, X, V2, V3, Y, X will output that polygon, and X, Y, V4, V5, V1 will output another polygon. So this is a subroutine, so to speak. I don't know if that word makes sense. It's a function call, right? It's a function that we know how to write. We should know how to write this, right? So how do we do that? How do we find out this point? How do we find out this point? The same way we find out this point, except that we work in 3D. Here we're working with 2D. Remember that formula? M1x1 plus M1x2 plus M2x1 upon M1 plus M2. Remember that? Right? Yeah? We use something like that. Okay? So all that which you sort of used in your 9th and 10th will start kicking in when you start doing these kind of problems. But in a more difficult way, and plus you have to write the program. There you didn't have to write the program. Right? There you just have to follow the instructions of the teacher. Okay, what has this got to do with the data structure? We'll come to that in just a second. Okay? So this is the binary space partition tree. Okay, the binary space partition tree is going to make a tree out of this soup of polygons. It's going to make a tree. The input is n polygons. You can think of them as n triangles or n polygons. The input is n triangles. The output is a tree, such that given the tree, a binary tree, it's going to, and given a viewpoint, it's going to give you a list of polygons such that you don't need the depth buffer to get the correct order of rendering so that you solve the visibility problem. Alright? How do we construct the tree? So we're going to pre-process the input polygons into a binary tree. No matter what the viewpoint is, it produces a sorted list of polygons that can be painted in back to front order blindly, but we are guaranteed that the visibility problem is solved. And it requires cutting as a subroutine, as a function call, which requires this M2x1 plus M1x2 upon M1 plus M2 business, except that will be in 3 dimensions. We'll consider the problem in 2 dimensions for understanding the algorithm, but it generalizes well to 3 dimensions, okay, for us to understand. So what's the idea here? Okay. So this is the crucial figure. So you need to focus on a little bit on the figure. Okay. So here is the same Z buffer figure that I showed you before, but now we're going to use a BSP tree. So here is the I, and we want to output the line segments. We have this soup of line segments. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 line segments. There were 11 triangles, 11 polygons. And we're going to output 11 polygons in a tree. Each line segment can be thought of as dividing points in a plane into an outside part and an inside part. Okay, so let's focus on line segment number 5. So what is it? We take the line segment 5 and we think of the line 5, which extends the line segment. And here is a point I, right? So what can we say? We can say that if the I was here, so we don't know where the I is, we don't know where the viewpoint is, but we'll just pretend, we'll make up one. So if the I is here, we can go anywhere, we can make it at the origin. Okay, that's a good example. We'll just pick origin and we'll say, okay, with respect to 5, 6 and 7 are on the same side as the I. So if I were to render 5 and 7, it's perfectly fine to render 5 first and then 7, because I know that 7 is going to overwrite 5. Is that okay? Right. If I just had 5 and 7, right, this is the equivalent of x less than y or y less than x in your sorting algorithm. Right? That's what's happening here. So you take this 5 and 7. Is it okay to put 7 before 5? Yeah? Let's continue here and let's think about line segment 9. What can we say about line segment 9? Is it okay to paint line segment 9, which is this one? Should we put it before 5 or after 5? Lady with the mic. Before 5, after? Okay, 7. I'm going to put it before 5. How about 9? Before 5, after 5? Who wants to before 5? One part is inside, the other part is outside. Right? This is a cutting example. Okay? So we'll cut 9 and we call this 9b and 9a. And we'll say 9a is before and 9b is after. Okay? So now comes the computer science part of it. Right? We'll start with the soup of triangles. We'll pick any arbitrary one. Let's say I picked 5. I'll put it on the root of the tree. On the left subtree, I'm going to put whatever is supposed to come before. On the right subtree, I'll put whatever is supposed to come after. And I will recurse. That's the algorithm. Trees are great because you can just recurse the algorithm. If one line segment, put it in the root, left subtree is equal to nil. Left subtree is equal to nil, right subtree is equal to nil. The recursion stops at that base case. Otherwise, loop through these polygons, loop through these line segments, and then figure out where they are. We know how to figure that out. We just did that in our 9th standard. So we'll do that. Okay. If necessary, we'll cut it out. We'll take a line endpoint, we'll take the other endpoint. If both endpoints are on the same side as the origin, we know it is before. If both endpoints are on the other side of the origin, right, ax plus by plus c greater than 0, right, we do the test, we know where it is. We substitute the point, we know where it is. Right? Remember that? We'll do something equivalent of that for 3D. Okay? And we'll make a tree. That tree works if the eye is at the origin. It doesn't work if it's at some other place. But we made a tree. Given triangles, we made a tree. Any questions on this point? Right? So maybe I have a picture for this. Right? So here we go. It's recursively constructed. We pick any arbitrary line segment, process it. Right? How much time does it take to construct a binary tree for n numbers? Right? You take, do a binary search done in linear time. Right? Time proportional to taking the input. So we'll do something like that. But here we have, cutting as a subroutine. So the number of triangles will increase perhaps. Okay? So the research problem is to figure out the optimal number of triangles. Optimal way of constructing this binary search tree. And obviously whenever there is optimal, there are people who say no, you cannot construct it, or it becomes combinatorically difficult and so on and so forth, and then some people come and say it's a clever algorithm. So if you want to follow on that research track, there are some problems there. But anyway, got this point? The basic algorithm. We pick an arbitrary node, we have inside and outside. And this will work. For example, here we have a tree, it says 1 is the root, 2 is on the left, 5 is on the right. So if I were to traverse this tree in order, left subtree, right subtree, left subtree, what am I supposed to do? Left, left, root, right, I get correct order, sorted order. Alright? Okay?
So the optimal tree building is equivalent to having a balanced tree?
Excellent question. The question is, what is the meaning of the word optimal? The optimal tree, see, this takes linear time if there are n triangles or n line segments as in our example. But we saw we need to cut. So maybe, just maybe, if I had chosen some other viewpoint, maybe I don't need to cut. Okay? How do I process a general scene so that the number of cuts is minimal, so that the size doesn't explode to something more than linear? Linear, 2 times linear, 3 times linear is fine. N square is bad. So optimal is like n raised to 1.7 or something like that. Okay? Something like that. Okay, so, but we haven't solved, what did I do? Go back. Go back. Go back. Go back. Okay. Okay, so what is the bug in this algorithm? When will this algorithm not work? 2 zeros in the score. When will this not work? What was the objective? Why did the Z buffer have a problem? Z buffer had a problem because we needed to update things very quickly. There are millions of points, hard to do this quickly, right? This is a better algorithm. What's the bug? Why is this not going to work? Why is this tree not a good tree for multiple viewpoints? Sorry? No, no, no. Forget about the cuts. That's a different problem. Assume the cuts somehow are manageable. Okay? Why? No, there's a basic fatal error in this algorithm.
For every viewpoint, we have to construct the tree.
For every viewpoint, we have to construct the tree. We don't want to do that. So if you use this tree for every viewpoint, what's the problem?
Searching the order.
Then we are finding left and right. If that figure itself is invisible, it goes back, then everything will go either in the right tree or in the left tree.
Not balance, nothing to do with balance. It's just not going to be the correct sorted order. You see that? Correct? We saw the example of the black triangle and the blue triangle, right? From this viewpoint, the blue is in front of the black. Clearly from the opposite viewpoint, the black is in front of the blue, right? And this tree will not work. Correct or no? Is it okay? So clearly it won't work. You think? Okay? But in fact this tree works. That's the magic of the algorithm. How do we do that? How do we make the same tree work for all viewpoints? How does it work for all viewpoints? Right? So this is what happens when Harry Potter is going on the, what is that game called? Quidditch. And they want to show it from another viewpoint. They rendered the scene completely and they want to render from here, render from here, render from here. So what is this person seeing? What is that person seeing? You want to render that, right? You want to be able to do that very, very quickly, right? So given any viewpoint, the order will be different. What he sees, does he see the podium? Does he see the podium? Right? That's the point, right? How do we do this? So, how do we make sure that this works from all viewpoints? So here's the idea. So we don't do, this is an in-order traversal, right? But we'll do a modified in-order traversal. Okay? In-order is, she said what? Left, root, right? We'll do it something slightly more clever. We'll start from an arbitrary viewpoint and we look at 1 and we say, where am I with respect to 1? Initially we constructed the tree in such a way such that if 2 is on the same side as me, then 2 goes into the left subtree. If 3 is in the same side as 1, it goes in the left subtree. Whereas if 5 is sort of behind 1, right, this plane which partitions, and if it's behind, then I'm going to put 5 on the right subtree. And that works from the origin, so to speak, as a viewpoint. But now we are given an arbitrary viewpoint and we ask the question, how am I placed with respect to 1? Right? Am I on the same side as the origin or am I on the opposite side of it? For the moment, assume this new I is such that it is on the same side of the origin. Right? Then what should we do? Should we look at, we want to produce the order. Remember, the order is back to front. That means, like the sorted order is, let's say 3, 2, 1, and then 7, 6, 5, something like that. Alright? Is that okay? So, if I am on the same side as 1, right? So it was constructed from the origin, but now I have a new I. And if the new I, and so when we constructed the origin, we decided to put 5, 6, 7, 8 on that side, and 2 and 3 on this side. And this is number 1. Correct? Now there's a new I, and the new I is such that it's on the same side as the origin. Right? Then what do you think? With respect to this new I, should I put 5, 6, 7, 8 on the right side? Or should I put 2, 3 on the right side? What should I do? Same. 5, 6, 7, 8. Alright? Now, so I now come to, let's say I decide to look at 2 now. It's immediate. Okay. With respect to, now there's 2 and 3 here. With respect to 2, if I was on the origin, as constructed before, I decided to put 3 on the left subtree. But now, with respect to this new I, I'm not on the same side as O with respect to 2. So where should I put 3? On the other side. Right? Here if I put 3 on the left, here I have to put 3 on the right. So that's the algorithm. It looks at each node. If I'm inside with respect to 1, I'll visit the right subtree first and then I visit the left subtree. If I'm outside with respect to 1, I visit the left subtree first and then the right subtree. Right? So the traversal is going to be a modified in order. It's not always going to be left, root, right. It's going to be sometimes left, root, right. Sometimes it's going to be right, root, left, depending upon where I am.
But don't we have to re-estimate the cuts?
That's the beauty. We don't have to re-estimate the cuts because the cuts are good with respect to the origin. Each point is either on the same side as the origin or not on the same side as the origin. If I get it right for the origin, I'm going to get it right for any other point because the space has been subdivided into parts such that they are mutually exclusive. It's a very subtle point, but that's where the beauty of the algorithm works. Right? If I decided, so let's get the basic algorithm and then we will look at the subtle point. So here we go. This is the algorithm. Once the binary tree has been constructed, this is the indexing as somebody said. Google has done it. We have done it. We have indexed it and formed a binary tree out of it. We perform a modified in-order traversal. Here is the pseudocode. Paint a BSP tree with respect to some arbitrary I. If b equal to nil, return. Whenever you write a recursive program, forget about anything else. Just look at the base case. Right? If you get the base case right, the algorithm automatically works. This is the magic. Okay? Base case. If b equal to nil, and how can this be so? That's how it is. Right? Proof by induction. If it works for n equal to 0, and if it works for arbitrary n, it will work for n plus 1. That's what's happening here. Okay? If b equal to nil, return. If outside b with respect to I, if I'm outside, this I is outside with respect to the root, go to the left, then the root, and then the right. If inside, then go to the right, then the root, and then the root. So as you go down this tree, remember there are a million polygons here. So this tree is going to be, if it's balanced, it's going to be log million, 10 to the power 6. Height is going to be 6. Okay? So it's nice structure. And then we're going to be able to do this modification, go back, left, right. It will not be going in a systematic way. It will go in this way or that way. Okay? Alright? Is this clear? Basic visibility algorithm. Okay? So let's go back to his point. Right? Will you need to recut? Right? So this is really the charm of the algorithm. Right? So you have some object, let's say 1, and you have an I. The origin. This is you are constructing it. And for some reason, you decide to cut an object. Okay? This is the object. Now you cut the object and you said that with respect to the line, this is, a line is a convex object, right? Either it's in front or at the back. There is no going in and coming out because it's convex. So a plane is going to be convex, right? So this is, you're cutting this into 2 parts. So A, X, B. Right? So with respect to O, you've decided to cut it. Right? Now, you look at any other point, right? See, I draw the point here. Again, when I look at it, sorry, it's bending a little bit. Okay? Right? It's this part only is going to be inside or outside. This is a convex object. Right? It can't be that for this you cut it, for this you cut it a different way. Because the cutting is a function of this object. It's not a function of the viewpoint. structure. It's a plane. It doesn't go like that or something. So it's going to cut this into two parts. This guy may be on this side or on that side. It can be on both sides. Now if it's a quadratic, or a cubic, it can go back and forth. But it's not the case. Alright? Okay? So, rendering, first step, figuring out the visibility. Next step, making it look as if it's completely real. Right? So you want to make it photorealistic. So, let me, so this is a construction of the binary tree. And this is a three-dimensional version. So it shows how to construct this in 3 dimensions. Do you want to see this? Raise your hands. Okay? Means what? You want to see what? Okay. So let's try to construct a BSP tree for this block. And if you can construct it for a block, we can construct it for another one, right? So this is from a particular viewpoint. Oops, I guess I don't have that. Okay. So for this tree, for this object, right, I'm going to construct a BSP tree. How do I construct it, right? Now there are multiple ways of constructing it. I motivated it by the origin, but we can actually do it another way, and let's do this the other way, so make sure we understand this, right? So the other way is that, let's say there is this three-dimensional structure, and we know instinctively that given this polygon number 2, this is the inside, this is the outside, and that's the inside of the block, right? So every three-dimensional block, which may not be convex, but if it's a structure, it separates space into 2 parts. There is the outside and then there's the inside, right? So on the right, I've shown how a BSP tree is constructed. Let's look at it, right? We start with, this is not a balanced structure, okay? So that's back to Professor Kamat's point, whether they should be balanced or not. It's not balanced, but it just illustrates the point. So we start with 1 arbitrarily. I named this 1. If I started with 5, it'll be more balanced. Let's say I start with 1, right? Then with respect to 1, right, where is 2, 3, 4, 5, 6, 7, 8? Well, 2 is with respect to 1. With respect to 1, where is 2? What is 1? 1 is this bottom part of this, it's a three-dimensional object, so there is a sort of a rectangle here, right? So 6, is it inside with respect to 1 or is it outside with respect to 1? Shout it out. 6. This polygon 6. So what is inside and what is outside? Okay? Think of this as a box, right? And if I'm I'm somewhere here, okay? I'm here, then I'm inside the box, right? So as far as this plane is concerned, 6. Don't get confused with this arrow, right? This is 1. Where is 6? Who said it outside? Say it loudly. Outside? Who said it? Who said inside? Inside. Okay? Inside. Inside. Okay? 6 is inside. What about 5? Inside. 3. Inside. 4. Inside. All are inside. Everybody comes into the left part. Okay? Look at 2. This is outside, everything else is inside. Right? The magic happens with 3. 3 is this polygon, this black guy. Right? With respect to 3, the inside is 4. Right? 1 is not in the picture, 1 has already been processed. 4 is inside. How about 5? Outside. Right? So 5 goes here. 6. Where is 6? 6. Outside. 7. What about 7? 7 is this vertical rectangle. Up, like that, like that. Right? Partly outside, partly inside. This requires cutting. This example that this gentleman asked, right? Cutting. So we cut 7. One part goes inside, one part goes outside. And so on. Okay? Alright? You can how does it look like this? Well, there is the first aspect of setting up that camera, figuring out how those polygons will appear if my viewpoint was here. Right? It won't look like this. It won't look like that. Right? The top view, for example, will look like a rectangle. Right? Just right on the top. Right? So that's a different problem. That's a linear problem. Right? Because all you need to do is take the dimensions of it and do essentially a matrix multiplication. Okay? That will do an orthographic projection or a perspective projection of that object. Okay? I'm not talking about that part. Okay? I'm talking about figuring out which is visible and which is not visible. Figuring out which is visible and not visible is a function of other guys, how they may occlude you. Figuring out what its shape is independent of what anybody else is. Okay? Alright? So, if I were to look at it from here, I'll ask the same question. If, for example, I'm here, then I'm inside with respect to 3. Right? So, the whole picture will look different. And we'll traverse the stream in a modified economy. Okay? I'm not showing that example. You want to see that example? I didn't put it in the slides. Okay? We'll see that later. Is that okay? It's fine. Alright? This is in 3D. Okay. So, I did first part, which is visibility. Okay? So, this is called an object space algorithm. The Z buffer algorithm required you to have a depth buffer which is of the same dimension as the rendering screen. So, if you do an HD display 1980 by 1080, 1920 by 1080, then you need to have memory which is like a million. So a megabyte of memory will go right there. It's not 1 megabyte because you have the red, green, blue channel plus the transparency channel, things like that, right? If you want to have a bigger screen, see, if you think about it, hard disk space has increased, memory has increased, CPU has increased, displays have not increased. Okay? If displays were supposed to increase at the same speed with which hard disks capacities have increased, a rendering algorithm would have to render a size of a football screen, and if you have a Z buffer, you need so much more memory to do that, you're going to have a problem. This is an object space algorithm in the sense that it returns output which is independent of the resolution, and then it makes a call, let's say, to some other scan conversion algorithm which is a function of the rendering. Okay? Plus, this has the advantage that you can change the viewpoint. But important thing is this is called an object space algorithm, that is called an image space algorithm. Its complexity is a function of the image space, and it's not truly correct because it's correct only up to a particular pixel. Theoreticians don't like the Z buffer algorithm because your depth buffer just has a binary value. Blue is in front of black, right? But you know, it doesn't happen like that. Suppose you were to make a super resolution situation, then now suddenly in the same pixel, blue may be in front of black. You may think this won't happen, but actually it happens a lot. Imagine a mosquito flying here and there, right? It'll come inside, come outside. You know, it can actually make things very, very jittery for you if you do an animation, and if this effect is not correctly captured. Suddenly you'll see blue color, red color, blue color, red color, you know, in your screen. It'll start flickering and your eyes will get tired, right? So the Z buffer algorithm is theoretically wrong because it's correct only up to a particular, it's like saying I figured out the intersection of two line segments only up to a resolution of 5 by 5. Otherwise, that's not how we learned our mathematics, right? We can compute this to infinite precision, right? We can give a mathematical formula and we can compute it to what level. This algorithm does not have that deficiency, and so theoreticians like this algorithm. Okay? Right. So I move on to another aspect, introduce that. It's more pictures and so on, and then we'll, in 20 minutes or 15 minutes, we'll break for lunch. Okay? Yeah. I generate the BSP tree. Actually, it a BSP tree which is pre-processed, you can spend whatever time you want in figuring out and making this as a balanced tree. And then that tree is good for any viewpoint.
No, what he's saying is, but there can be several BSP trees that can be generated.
Absolutely. Yes, absolutely. There can be many BSP trees that can be generated.
Is there any paper?
Yeah, so you want to make a BSP tree such that the number of splits is minimum. So you figure out some point from which the splits is minimum. So n, if n is the total size of the object, then n should not, ideally, best case scenario is that the tree has exactly n objects or linear O of n objects. But there are no, so that cannot, people have not been able to do that. So it's something like n to the power 1.5. So I will guarantee you that there is no more than root n overheads to create this tree. You give me a bunch of polygons, I'll figure out where to place my viewpoint so that I don't have to cut so many times. That's the theoretical problem. Beg your pardon?
It's not NP.
No, it's not. No, it's polynomial. Yeah. Okay, so it's not NPR, but there is a cute approximation algorithm which is around this number, almost linear. So it's some n log n something. Okay, so let's move on. And now I'm going to talk about the other aspect of making rendering in answer to her question. So I've solved the visibility problem, but what is the color, right? Now the color of an object depends upon the illumination in the scene, depends upon the material properties of the object, and depends upon the viewpoint. Okay? I'll repeat this again. The color of an object, yellow color, depends upon the light. If there is red light, this yellow object will not look yellow. Right? That's what we see in some dramas or in dramatics. It depends upon the material of this object. This is yellow, this is kind of yellow. Okay? But obviously these two yellows are different. And also, presumably depends upon where you're looking at. Let me explain, show that in this board, right? Depending upon where you are, you will see a reflection. This is white, but in some places it's more white than others, right? Depending upon your viewpoint. Where do you see the bright part? Here? Here? X? Okay. Where do you see the bright point? You see a bright point anywhere? This side. Same object. From the factory it came with the same color, but it looks bright here for her and different. Right? So the color of an object, for it to look photorealistic means it should look as rendered by the computer like it looks by that camera. Right? It should be the same. If you do a diff, it should be 0. Right? So you have a file, you say diff AB, it says 0, you know that the answer is correct. Right? You don't want your salary to be less than another person's salary. Same thing. We don't want the camera to report a number which is different from this. That's sort of the goal. And that's a hard problem. That's a hard problem because we don't know the physics that well. But we approximate. So that's what the first line says. The intensity of a point P depends in general on where the light source is. What is the color? It's yellow. And where is it? Here or here? Where the viewer is, where I am, this looks different based on this compared to something else. See, why do we use a laser? We use a laser because it doesn't depend upon, everybody knows where I'm looking. There's no confusion. If I point like this, you don't know where I'm pointing. Okay? So, the laser is a coherent source of light of a particular wavelength, right? And what's the downside of the laser? The battery doesn't make it run out, right? So, coherent and it just goes at one place. It's one place, right? At that point. But light sources are not like that. And you you want to be able to simulate light sources. So we make simplifying assumptions, okay? And humans are less sensitive to certain kinds of errors and more sensitive to other kinds of errors, and that helps the simplification process. And here, graphics and vision, computer vision, starts kind of overlapping much more, right? Because in vision, we are trying to do the same thing. We're trying to find the depth of a scene based on the color. So, OpenGL, so Turbo C, which is where you learned your programming, right, doesn't do illumination models. It doesn't tell you. When you red, it says red color, okay? OpenGL is what most people use, in fact everybody uses OpenGL, to get slightly better effects, right? And labs and other places use ray tracing and radiosity, which gives you even better results, okay? Very sophisticated games, which typically does not run on your old computer. Has that happened to you? एक गेम इस पे नहीं चलता है, होता है क्या? Yeah. Those guys use GPUs to do more complicated calculations so that you get that simulation. So we'll see more examples of that. But let's do the simpler first. So we'll do the simplest type of things first. Okay? Let's show some pictures here, right? So here is some scene. We kind of can understand the three-dimensional nature of this. We kind of, for example, say that the teapot seems to be behind this object. Maybe this cone is, I don't know, in front of this sphere. This kind of gizmo here, I don't know what this gizmo is. There's a table lamp here, presumably. Seems to be floating in space, but actually there is a stand here which you can't see because of the light. Lack of, or yeah, we should be more dark here. And now here, we have solved the hidden line problem. Okay, we've solved the hidden line problem, and now we can clearly see that the teapot is indeed in front of this kind of star-shaped object, and this cuboid object which you see here is indeed in front of them. Right here, we can't make up. Right, that's what we solved just now by Z-buffer or DSP trees. Right, we solved that problem. Okay, but we still don't like the scene. It's not enough. Why is it not enough? Well, you prefer that one, you prefer this one. This one, right? So what we have done here is that we have done it the way Turbo C would shade it, right? It does constant color per triangle. It does not take into fact that the properties of an object depends upon where somebody is looking. Like this is uniformly blue. There is no variation in shade across this. This is uniformly orange. There is no variation across it, right? It doesn't do that. So, constant color per triangle. Every triangle has one color, right? We give the illusion of 3D by making this a little bit darker. We give a different color to this guy than to this guy. But across this, we are not giving different kinds of blue. Okay? This is important. How can I motivate this statement? Let's take this mouse here, right? So if you look at this mouse, it looks supposed to be black from the factory, but depending upon where I put it, forget the silver part, it looks white, right? It's black, but it's white. Okay, gentlemen, when you go looking for a blouse for your wife, be careful. Go to the market and buy a color. My wife comes back and says, "That's not blue." I said, "That's what blue to me. It's not. No, it's not matching." Okay, it's black, but it's white. It's black. It's white. Black. White. Okay. So we want to have the same surface, have different colors, right? Just give me a second while I put this mouse back. This is a design problem, right? How many of you have a problem with USB? Okay. All right. So, how do you fix this? This is called flat shading. You can think of this as Turbo C shading. One color. kinds of blue for this block. Think of a cube. It's your job as a programmer. If you program this with the same blue, what is the color of the cube? It's blue. Let's call this a cube. What is the color of the cube? It's blue. If you paint it as blue, 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 it will appear like a hexagon. It won't appear like a cube. Because the human eye cannot tell. It is expecting some changes in color. You see that? Right? You take a cube and ask the color from the user. User says red, and if you don't program it correctly, it will look like a hexagon. You say to the teacher, this is a cube. She says it's a hexagon. Cube, hexagon, right? How to convince her that you have actually done three-dimensional rendering? Answer is paint different colors for the different faces. That, even though it's the same red, okay? Slightly different variation. How to get the different red? We'll see after lunch. Okay? Or maybe now. Alright? Let's go on. Here is something called Gouraud shading, where you see this thing. It appears to look more natural. You can see some shading here coming up here. Right? So look at the previous one. The shading was there, but it was more direct. So this looks like a pyramid. It doesn't look like a cone. But oops, sorry. I got to fix this. It's not working for me today. Okay, sorry about that. So this doesn't look like a sphere, right? But when I do this the right way, it looks like a sphere, or it looks like a cone. This looks like a cone, right? It's a cone. Mathematically, it's a cone. That is that we want it to be a cone. Based on what was said earlier, if you do a Bezier curve, if you don't do the correct number of interpolations, number of in-between points, it will look like a pyramid, not like a cone. Okay? And if you do the correct shading, it will look like, this is called Gouraud shading. Okay? I'll explain how this works, but I just want you to appreciate this for the moment. And now, this starts looking like a shiny cone rather than a regular cone. Starts looking like a shiny cone. Okay? So if we want, we ask from the user, where is the light? Is it orange light or is it white light? We ask from the user, is it a cone or is it a pyramid? Right? And we ask, where is the camera? That is, where is the person looking at it? And based on that, we decide, based on the material properties, is it a shiny cone? We want to make it look like this. Shiny, non-shiny teapot, shiny teapot. But then this looks much nicer on the laptop screen. A little bit of low pass filter happening. Okay? Alright, now you can see the stand here a little bit more clearly. Earlier it was. Questions on this? There should be some questions. Yeah.
What is your lab set? Has two speaker
Why does it have two specular? Okay. So presumably there are. I mean, he's observing that light should, like for example, here the light is coming from the front, so there is one specular reflection. Here there is one specular reflection. I mean, specular reflection is the shiny spot I was showing you on the mouse, right? That's the specular reflection. And he's saying like, why is it having multiple things? And the answer is I have no clue. Okay, but I can speculate why it could be the case. When we do this, we can also think of a light source inside in addition to the light source outside. So if you want to render a lamp as if there is a light source inside, so then it's possible that we can generate something. But for the moment, the idea is just to show you. Or maybe there's a light source coming from here and a light source coming from here. Okay, so multiple light sources, so that's possible. Any questions on this? Sorry. Questions from the students? Must be. Other than when is lunch? No questions? You want to know how this is done, or you don't care? Huh? Yeah? What? I don't know. What did he say? I'm just asking you, how do you make the difference between these two things? Okay? I'll show you that later, maybe. Okay, and here is one more picture. It's called form shading. And the specular part is even more pronounced here, and I guess it's still more pronounced here. Okay, and this starts looking like a projector, it's more shiny.
So one question here.
Yeah.
Just as a sphere, you can see the bottom part still not circle.
Oh, the bottom part is still not circular. Yeah. Yeah. I mean, this is coming because there is actually a shadow that is being shown. So the shadow of that object is probably appearing here. This is not the object. There's probably a shadow created. Should be circular. This is from the book that was mentioned, Foley and Van Damme. It's copied from there. Okay, it's not my picture. My picture would be better than this. I have no problem saying that. Okay, Foley and Van Damme, they wrote the book 1980s or something like that. Okay, very smart people, much smarter than me, but they wrote the book much earlier when we didn't have, I don't know, we had kilobytes of main memory, things like that. Completely different type of situation. Okay, so I'm going to stop here. Okay, so I'll let you go for lunch. And the game plan is, so I've covered visibility, I've covered part of the rendering, but I've not covered ray tracing and radiosity. I'll kind of leave this here at this point. Maybe Professor Kalra will come back and talk about animation after lunch, so we'll decide how that's going to work. And so the plan is that we will do a little bit more of ray tracing and radiosity, and then do Harry Potter and the complex numbers. Okay, for those who want to hang on to the end. So we'll break now for lunch unless the organizers have any other announcements. We'll come back at 2 p.m.